Hi, my name's Jim Huguenin. I'm an architect working for Microsoft. My primary responsibility is actually roughly the same as the title of my talk. It's making sure that we have a great story for dynamic languages running on top of Microsoft.NET. And I want to tell you a little bit about how we do that and what sort of story we have. When people think about dynamic and static languages, this is often the picture that comes to mind. There's a war between these two contingents. Now, how many of you were at Anders' talk just before mine? Yeah, so I think he took my punchline away. That's OK. If I'm going to give my punchline up to anybody, that would be my first choice. The punchline is you really shouldn't be seeing this as a war between these two worlds. If you can bring the two worlds together, they each have a lot of good things behind them. And we all would much rather see this story than the other one. And that's what we're trying to do on top of .NET, is bring the dynamic and static languages together so that we have peace between them. And you can use whichever language is appropriate. And if you have a library written in a dynamic language, but you happen to prefer writing in a static language like C#, well, we're going to make that really easy to do. If you want to build your code in a dynamic language and go run it on an ASP.NET server, we're going to make that really easy to do. Whatever you want to do, you ought to be able to use the language of your choice and the one that's appropriate. I find most good programmers who I've ever worked with know more than one language. And they typically know a language that's statically typed and one that's dynamically typed, and quite possibly a few others with some weird behaviors. So the way that we're trying to bring these languages together on top of .NET is by providing this common piece, this dynamic language runtime. On top of the dynamic language runtime, again, this is a repeat for some of you, you'll see traditional dynamic languages like Iron Python and Iron Ruby. These are implementations of these dynamic languages that have been out for a long time. You'll also see traditionally static languages like C# or VB.NET taking advantage of these dynamic features in order to work very well with dynamic capabilities now available inside of .NET. And other languages we expect to be showing up. There's already a lot of projects out there. Iron Scheme seems to be the one with buzz at the moment. But hopefully we're going to see a lot of languages built on top of this platform. Now, underneath it, all these languages, through the dynamic language runtime, can talk to a lot of different kinds of systems on the back end. They can talk to .NET objects. They can talk to JavaScript objects through Silverlight. You saw a demo of that earlier today. They, of course, could talk to Python objects or Ruby objects or COM objects, and that way be able to communicate with things like Office. Now, the features that make this work, and the main part of my talk is going to be about explaining each one of these features to you, are these three key features in the dynamic language runtime. Expression trees, which gives us a wonderful way of dealing with code at runtime in a very easy to understand and analyzable way that also can turn into wicked fast optimized machine code thanks to the CLR at the end of the day. A shared notion of dynamic dispatch, so that all of these languages can communicate with each other and can communicate with dynamic objects all now in the shared way. This is the same way that the CLR brought a shared notion of static dispatch to the world, so that all the static languages could work with objects from each other. We're now adding that with a shared notion of dynamic dispatch. And this mechanism of call site caching to make sure that the dynamic dispatch runs relatively fast. Those are the key features in the DLR. I want to give you a little bit more background before I talk about it. Does this remind anybody of my first slide? War? No. This is another place where there's traditionally some animosity in the world between commercial software and open source software. The DLR, this is another gap that the DLR is trying to bridge. The DLR has grown out of our work with Iron Python and Iron Ruby. These are traditionally open source languages. In order to work with these communities, we've built both of those implementations in an open source manner, under an open source license approved by the OSI. This is their logo, so I get to use it. And for the DLR, because these dynamic languages have this history of open source, we want to do it the same way. We also want to do it open source because it's about language implementation. And we want all the language implementers and library implementers who want to build on top of it to have full access to the source code in the DLR and to be able to make changes if they want to in order to make their languages work better. So we're bridging that by releasing the DLR in two different worlds. You can get the DLR both on CodePlex under the Microsoft public license, which is an open source license, and as part of the .NET Framework 4.0 and Visual Studio 2010. Okay, there's two different sites that you get them from. One is this site on CodePlex, codeplex.com/DLR. The other one is in the official Microsoft releases. You should have a PDC drive with a CTP of Visual Studio 2010 that has a version of the DLR in it as well. Now, the open source version is going to have more rapid releases. The sources are always going to be live. That's a typical feature of an open source project. The official releases are going to be much more thoroughly tested and are therefore going to be on a slower release cycle. You get the benefits of both. You can pick which one you want. The code, these trees, sites, and binders, the key components of the DLR is the same. It's equivalent on the two sides. We're not giving you different code on the open source side as we are on the commercial side. On the open source side, we are building things that aren't ready for the framework yet. We have shared hosting APIs that we'd like to see in the framework in the future, and we're building those on Codeplex. And you can get those now and start playing with them and have fun with them. We hope that those things will wind up in the framework in the future, but this gives us a place to experiment out in the public and get your feedback very early on what we're doing. And of course, there'll be things that are only on the commercial side. So C# 4.0 with dynamic that you saw, VB.NET 10, both of them have support for these features, and they're only available through the commercial release. So I need to quickly tell the story about how I got involved in dynamic languages. The inspiration for me coming to bring dynamic languages to .NET actually came about 5 years ago, reading all of these reports on how horrible a platform .NET was to run dynamic languages on top of. There are people saying, you know, we built implementations of languages on top of this, and it ran horribly slowly. It's not useful for anything but demos. And I felt very sad, and really what I wanted to know was how Microsoft had screwed up the CLR so badly that it was worse than the JVM for running dynamic languages. Because I knew about 10 years ago, I started a project called Jython, which ran Python on top of the JVM. It was never quite as fast as the C-based implementation, but it was fast enough, and it was good enough that people were using it in production systems. I thought, well, if the JVM can do it, how did Microsoft make the CLR so bad for dynamic languages that it was even worse? So I was going to take a couple weeks, build a few quick prototypes of Python running on top of the CLR, and write a little paper called Why .NET is a Horrible Platform for Dynamic Languages. It didn't turn out that way, or I probably wouldn't be here at PDC. I don't think that talk would have gotten accepted. Instead, here's what happened with my prototype. And I want to show you, this is the standard Pystone benchmark. You can argue about benchmarks for weeks on end. This is the one benchmark that ships with every version of Python. Higher numbers are better. And each successive version of the C-based implementation that I'm showing you here gets faster on it. And what that means is that the people building Python implementations care about this benchmark, and they make the implementation run faster each time. When I built my rough 6-week prototype of IronPython on top of this, I found it was even faster. It was way faster than the C-based implementations, which wasn't at all what I was expecting with my Jython experience. I was expecting to be close. And since then, I've joined Microsoft. We've taken IronPython to the 1.0 level. It got even faster. It's actually a great story about how it got faster. We did virtually nothing in IronPython itself to make it faster. The reason that it got faster was .NET 2.0 made delegate calls a lot faster. And we were able to just ride that wave. Because they put this performance improvement in the core .NET runtime, IronPython got faster. And this is part of the story about why you want a shared framework for building your languages on top of. All of that work was done to help C# and VB developers. Nobody was thinking about Python at the time, but it wound up benefiting Python tremendously. And we want to see a lot more things like that happening in the future. OK, so running fast is good, but that's not really what gets me most excited about running Python on top of .NET. This is what gets me most excited. And unfortunately, you guys can't see this slide very well, so it's going to be hard to explain. Let's zoom in on this part. This is an example of the standard code for extending Python with C. I took this code directly from the Python tutorial that ships with Python. And this is how you would add some code in C in order to add some capabilities to the Python language. Now, I could spend the next 30 minutes explaining to you what this code does. Or I could show you that code translated to C#. That's that page of code. That's what it does. That's everything that it does. Of course, it's not quite everything that it does, because the C code's dealing with the mismatches between C's garbage collector and Python's garbage collector and trying to match them up. It's dealing with the mismatches between Python's object system and C's pointers and trying to match them up and marshalling things. So it's doing a whole bunch of work, but none of it's interesting except for that. And the beauty is, by running on this common platform, this is now the way you get to think about interop with languages rather than that horrible picture of C that it used to be in the past. Now, the other part of this notion is, just writing code easier is a good thing. But having the code live in one world takes away a lot of pain. Again, with Python and C, you have Python objects living in one world, one garbage collector. C objects living in another world, no garbage collector. Every time you pass data from one to the other, you have to talk to the garbage collector. You have to do marshalling between the two different worlds. You pass data back. Same thing. You talk to the garbage collector, you do marshalling back and forth. And once you get one of these, if you ever actually have a circular reference between the two different worlds, you should talk to the world's leading experts on garbage collectors, and they start to look, in serious pain how to solve that problem. On top of .NET, we're able to bring the two worlds together into one. Now it's one world, one garbage collector, one set of standard objects. There's no marshalling that goes on. The two languages can live very nicely together. So to kind of finish the main talk about IronPython, and you're going to see just how much IronPython there is in this talk. I apologize for that. Part of why I'm not going to show you too many IronPython demos today is Anders actually stole most of my really good dynamic language demos. If you looked at the end of his C# talk, that's been what we've been talking about dynamic languages doing for a long time. And that's wonderful. And the fact that he stole them is wonderful. And that's the whole point of this talk, of bringing them all together so that all of the languages can get better. Still, I feel it's important to answer the question on when to use IronPython, at least by telling my own personal story. So when I was building IronPython itself, I had to decide what parts to write in Python and what parts to write in, what language to write it in. What I did was I built these 3 prototypes in 6 weeks, and I wrote them all in Python. Not in C#, not in C++. I wrote them in Python for the rapid interactive development that I could do. These dynamic languages are extremely nice for rapidly developing prototypes. Not having to specify the types in your system is something that gets out of your way when you're trying to just conceptualize what the structure of the problem you're trying to solve is. There's no way I could have written 3 prototypes in 6 weeks in any other language. I could have. Other people might have been able to do differently. And it had existing libraries that worked for me. In this case, the Python parser is a pretty good example. Now, it's interesting. People have asked me, so I wrote IronPython in Python, but it was all about running Python fast on .NET. How does that work? The way that it worked was actually my prototypes all generated C# source code that I then statically compiled in order to figure out that things worked. And that's another case where these dynamic languages are really good for doing lots of text manipulation. So my compiler was generating C# source code, and the dynamic language was a really good choice. Now, the prototypes are great in Python, but the production's actually built in C#. This is a case where I see the benefits of both worlds. The production system has a team collaborating on many lines of code. For me, in that case, the enforced modularity, kind of the rigid structures that you get with type systems, I find are very valuable when you have a large team working on code. And it's shared framework code. It's shared framework code that's turned into the DLR that we want a lot of people to be able to use. And static languages work very well for building this kind of shared framework code. So I found benefits in both. Even today, though, the infrastructure for IronPython is still built in Python. IronPython, actually. So we're self-hosted, and all our test suites and testing tools are a wonderful place to use a dynamic language, even on the largest projects. Our build and deployment scripts are also built in Python. And for me, whenever I want to write a personal tool to do something fun on top of .NET, it's written in IronPython. So this is my story. You'll find people who have written 3 prototypes in 6 weeks in just about any programming language you can find. You'll find other people who are building large production systems with lots of developers in dynamic languages. This is not trying to be prescriptive. I just wanted to share my experiences. Now, anybody in the audience upset that I haven't yet talked about this other dynamic language, Ruby? Well, I don't have very many of you to apologize to then. But I will nonetheless, to those who raise their hands and say, if you wanted to hear more about Iron Ruby, John Lamb is giving a talk in room 515B today at 5:15 p.m. just after this talk. So you're going to get a lot about Iron Ruby. The other thing about John's talk, I should say, is I'm not going to give you any more demos of the cool things you can do with the dynamic languages. I'm going to tell you about how it all works under the hood. John's talk is going to show you a lot more about the cool things you can do with dynamic languages in .NET. So even if you're not interested in Ruby, but you want to know some of that, go see John's talk. And now I get to stop talking about Ruby for a while, which will simplify life for me. Not that I don't like Ruby. Now, my last bit on Iron here, this is a question I get at the end of every talk I give, so I thought I would just put it up front here, which is, what the heck does Iron mean? And it's interesting. I came up with Iron 5 years ago as I was trying to come up with a name for this project. Part of it is Iron is not language.net or language sharp. Those were 2 ways that people had named languages in the past that were running on top of .NET to mean I took this lovely language and I changed it to be something else that ran really well on .NET. And I wanted to have some name that meant something different. It may also have had to do with the fact that I have a guilty pleasure in liking Iron Chef, but we won't go into that too deeply. So what Iron means is it's a true implementation of a language. It's true to the language. Okay? It matches the language's specification. We don't change the language's specification. It runs the language's regression test suites. It's true to the community. So with IronPython, Microsoft's a member of the Python Software Foundation. We communicate with the Python developers. We talk to them about improving the language. We're not creating our own new community. It's true to the experience. So we have things like a redevel print loop that's not going to be unique to Python or dynamic languages for very long. But we provide all of those things rather than saying you should just use static compilation with Visual Studio projects. And it has excellent performance, of course. But it's also great integration with .NET. So it's easy to use .NET libraries. It's easy to use with other .NET languages. It's easy to use in .NET hosts. It's easy to use with .NET tools. That's the meaning of Iron. For those of you who want a slightly more formal definition of it, you can think of it as implementation running on .NET. I think I'll move on to my next slide at this point. The question was, did I make that up beforehand or afterwards? And I think I will invoke the fifth. So now to get into the meat of the DLR and the dynamic language runtime. And the key part to start here is this is just the next stage in the evolution of the CLR that started about 8 years ago. With .NET 1.0, we released a common language runtime that had a lot of features that programming language needed. It had a very high-performance JIT, a GC, a standard class library reflection, dynamic code gen, verifier, sandbox, all sorts of things that programming language implementers would ordinarily have to build themselves and spend a lot of time building second-class versions of. Now, .NET keeps getting better on each version. So in .NET 2.0, we add more features to make it a better platform for languages. This time we added dynamic methods so that code gen could be collectible. We added generics in the runtime, which was a great thing to do, so we both got performance benefits out of that, and we had generics so that dynamic languages could understand them too. I love the fact that dynamic languages can work with these very functional generic types. And we made delegates faster. I mentioned that earlier. That helped all the dynamic languages. So in .NET 3.5, we added more features for language implementers. We added extension methods and expression trees, and OK, this one's a little odd, so I made the shape different. But we added a new way to run your code called Silverlight so that you could run your code in a browser. And all the languages running on top of .NET, again, got to take advantage of these. We called some of these Link. This is just part of .NET 3.5 that made it a better platform for people building languages. Well, in .NET 4.0, we're adding more features to make it a better platform for people building languages. You should go to the .NET 4.0 talk to find out about the ones that are not in this box, because these are the ones I'm going to talk about. The parts that we're calling the DLR. But this is just the next set of things we're adding to .NET. Again, dynamic dispatch, expression trees, and call site caching. And we're not done, right? That's the other thing why I think .NET is such a great platform for building languages. We're not done. In the future, I told you, we have some prototypes of script hosting that we have on Codeplex that we're going to bring into the platform. Anders showed you those compiler as a service APIs that, again, we're going to make available to language implementers. And there's going to be more. But for now, let's step back from the future and talk about these parts of the DLR. I'm going to tell you first about dynamic dispatch and how shared dynamic dispatch works, then about the next version of expression trees and what we've added to linked trees to make them powerful enough to represent at least full method bodies and everything that we need in order to do dynamic languages effectively on the platform. And finally, tell you about call site caching and how we make it all go fast. OK, so without further ado, let's talk about dynamic dispatch. Yeah, I get to spend a lot of time on this slide, right? OK. So as you all know, this is what it looks like to call a static method in C#. It's really ugly to do that with reflection if you want to do it late bound. And it's ugly in yet a different way to call a JavaScript object. So in C# 4.0, we've made it elegant to work with these kinds of dynamic libraries. And we've done it, and I just can't get over saying this, by adding a new static type called dynamic. Been working on this for over a year now, and it still tickles me that we added a new static type called dynamic. The beauty about adding it as a static type, though, is C# is a statically typed language, and types flow throughout everything. And by putting dynamic in as a type, you're able to make dynamic flow throughout everything. And it's really a beautiful way to make it deeply embedded. But I'm not going to talk about C# language design here. I think there's others who can do that better than me. Instead, I'm going to talk about this part of the dynamic method invocation. So C# now has dynamic method invocation built on top of the DLR, and I want to talk a little bit about how that works and how you're able to get language interop by having this dynamic method invocation built on the DLR. OK, so the way that this works, you've all seen this picture before. you have the dynamic language runtime, and languages can be built on top of it. In this case, I'm showing you IronPython, and it might have code that looks like x.foo. It can translate that into a standard message that the DLR understands. Get member is one of the standard DLR messages, and I'll show you what they all are, of the member foo, and you know what? It's a case-sensitive language. So it has this standard form that Python can represent it to, and then it can use that to talk to a Python binder and get correct Python semantics. Well, that's an awful big layer of indirection we just stuck in place for Python code in order to talk to Python objects. But that same code can let it talk to .NET objects and all of these statically typed .NET objects, and there are one or two interesting ones in the world like WPF, WCF, there's an awful lot of interesting statically typed objects, so by making those available to the dynamic languages, that's great. It can also talk to things like, it can use COM and talk to Microsoft Office, again, by having this layer of indirection. Now, the Python developer doesn't have to understand COM. They can use the DLR to talk to these other kinds of dynamic libraries. When we add more languages like Iron Ruby, it immediately gets all of those capabilities underneath. So Iron Ruby can now talk to .NET, can talk to COM, can talk to Python. I think we forgot something. Yeah, better add a Ruby binder so it can talk to Ruby, or it would be the weirdest Ruby implementation ever. And we add languages like C# and VB.NET. They, again, can talk to all of this infrastructure underneath, and they don't have to rebuild it. So we've solved this n times n problem of language interop, where every language has to understand everything it wants to talk to by putting the DLR in the middle and turned it into a 2n problem, where you just need to build the binders and the languages. And up top here, let's see. Oh, yes, VB.NET had an ignore case set to true, by the way, in order to make sure we have the correct semantics of the language. You can add other languages. That could be PHP or Perl. And, well, they're going to set ignore case back to false. But the part I really want to talk about here is you can add your own binder to down at the bottom. And I want to show you how you can write your own binder so that all of these languages, including C#, but also including Python, Ruby, VB, and other languages that may not have been invented yet, can talk to your library. So in order to do this, we need this set of common actions. And I want to show you the full list of common actions that the DLR has. I know this is a boring list to go through, but one of the keys to getting language interop to work is to figure out what are the common operations across languages. The CLR spent a long time figuring out how to do this for the static languages. We spent a long time figuring out how to do this for the dynamic languages, and I think we have the right list. The basic operations that we found are get member, which I mentioned, set member, surprise, surprise, and delete member. Now, not all the languages support delete member. That's OK. We still think it's important to have in the common set so that those languages that do have delete member can all do it the same way and can interoperate with each other. If you choose not to play, that's fine. Ruby's a little verbose for delete member, but I'm not going to hold that against them. Then we have the unary operations. Here we're using exactly the set of unary operators that are available in link expression trees. We have binary operators. Again, exactly the same set of binary operators as are in link expression trees. And we have conversion operations. Type conversions are a dynamic operation. You can overload type conversion. Hence, a dynamic language ought to be able to participate in it. It turns out the truly dynamic languages don't have syntax for this. It's not a concept they know of, but the static languages do. Again, that's OK. We have method calls. I used to believe that method call didn't exist. Python always treated method call as get member and then call that callable object that you get back, but the rest of the world convinced me I was wrong. So we have method calls. We have invoke, which is like calling a delegate. Ruby has slightly odd syntax for this. It actually has 2 or 3 syntaxes for this. This is calling a proc. We have create instance, which is doing new. And if you remember Anders' demo earlier, this is the one place where I think the C# story is not quite done yet. They don't have a dynamic version of this, and I suspect that that will change before we are done. And then we have get index, set index, and delete index for completeness. So that's the full set of operations that we're providing on the DLR. And we believe that with those operations, you can build up what languages need to do later. Now, if you want to play in this world, the easiest way to do it is to implement this dynamic object type that Anders told you about. Now, I'm leaving it up a little bit longer than he did, because this is the deep dive. This dynamic object has methods that correspond to all of those standard actions that I showed you. So for every one of the standard actions that you can do in the dynamic world, there's a method here that you can implement. So if you want to figure out how you delete indices on your object, you override the delete index method. That's all that you need to do to play in this world. At the very end of the talk, I'm going to explain this last line for those of you who really want to play deeply in the world. But let's start off with the simple part. Now I'm going to show you a demo of C# 4.0, IronPython 2.0, and the DLR working with dynamic object. Let's see. Can everybody see my Visual Studio? Great. I never know now that I'm back here. So what I'm going to do is create a bag class, just like Anders did earlier. I'm going to take it a little bit slower, and I'm going to add a few more things to it before we're done. So what I need to do that is I create a bag class, and I want it to implement this type dynamic object. Now I'm going to give it a dictionary going from strings or names to objects that holds on to all of the data, all of the values that are set in my bag. So I'm going to be able to create a property bag of name value pairs here. And let's make my Visual Studio a little bit bigger so that I don't have scrolling issues. Now I start by overriding methods. So the first method I'm going to override is getMember. I'm going to override the getMember method to say what should I do, and well, I want to return a value out of my dictionary. I'm going to reach into the dictionary, and this info action that I have coming in has a few properties on it. It basically has name and whether or not to ignore case, and I'm going to ignore ignoring case for the purposes of this demo. That just trips off the tongue, doesn't it? And then I'm going to override the setMember method, which is pretty important because if you can only get members, the object's not going to be very interesting. And it's going to do the same thing of set according to the name of the member that I want to get, the value into the dictionary. So this is all that I need to do in order to be able to implement a property bag. And now I can use this property bag from C#. Okay, same idea, and again, same thing you've seen before with slightly different words. Bag.age equals 8. I think C# 8 years old. And we're going to write something out to say, is years old. And let's use bag.name again, and bag.age. So here I'm able to create whatever properties I want to on the object, put them into the object, pull it back out, run it, and I'm able to tell you this lovely news that C# is 8 years old. Great. Everybody excited to learn that? Anders got applause. Yeah, second time around. Oh, pity applause, pity applause. There's nothing better than that. Now I need to extract this out into a method. Same idea so that I can use it again. I love the fact, and this gets back to, you've seen this before, but it bears repeating. Because we put dynamic into the type system, everything flows nicely through. So when I do a refactor like extract method, I get the dynamic type pulled out. I'm going to make this method public so I can call it from other languages in the future. And now what I'm going to do is I want to add methods to this to show you how you would add the ability to call methods on this bag type. So we're going to go back to bag, and I need to override another method. This is in order to do the invoke member action. So invoke member is our generic form for a method call. The idea is you're going to invoke something, you're going to call something that's a member on the object. So it's going to have a name, which is available here, and it's going to have a set of arguments. Now the first thing we're going to do is get, hopefully, some callable object that corresponds to the name that I ask for. So I'm going to create a dynamic target. I'm going to pull out of the dictionary whatever the name of the method is that the user asked for. Now, in order to call from C#, I need to switch on the number of parameters, because C# doesn't have call syntax that unpacks parameters into a call. A lot of the truly dynamic languages do have that, but we work with what we have. We need to reserve something to the dynamic languages. And now I can do, if I pass it 0 arguments, I'm going to call the target with this, with the current object. So I pass it self, so it has access to it. And if I pass it 1 argument, I'm going to call the target with this and arguments 0. And now I will spend the rest of the talk adding in 12 more argument types. maybe I'll just be lazy, since I happen to know what I'm going to use for the rest of the talk. But you can use, I'll leave it as a very simple exercise to the reader to extrapolate this to more arguments. So now I have my bag is able to invoke members on it, so long as I put something callable on it. So I need something callable to put on my bag. Well, let's use a delegate that I create from C#. I'm going to create a little delegate, call it hi, and we'll just do an anonymous delegate here. So now I have a little anonymous delegate that takes in some object, and when you call it with the object, you can write things out to the console. I'll try taking a question. I may ask you to hold them to the end later. Yeah. So there was a question about, in invoke member, could I delegate to another iDynamic object? And the answer is absolutely yes. I will save that for the end of the talk, though, because you need a lot more mechanism in order to do that properly. And I will hold questions now until the end of the talk. I think that that'll be a good idea to keep things moving. So I've created this little callable delegate. I can put it on the bag as say hi. I have a little callable method now. And now when I go to invoke a method, the say hi method, what this is going to do is it's going to go back to my bag. It's going to pull this hi callable delegate out. It's going to say it was called with 0 arguments and call it with me. And I should say hi. So now you get hi from C# coming from the bag. Now I want to add a little bit of static typing into this, again, just because I'm so tickled by how well the two worlds work together. So I can add another parameter to this method. And this is going to require moving things onto new lines and refactoring my anonymous delegate. And now I can set the foreground color to be this new method, this new color that I'm passing in. If I go down here and pass in a console color, we'll do dark magenta today. This will flow into the callable delegate, and all the arguments don't need to be dynamic. This one's fully allowed to be static, and we should see a dark magenta hello from C#. Of course, I forgot to set the foreground color back to black, but you'll all forgive me, I suppose. And this works even if, so this works if I statically type it, and this same thing works if I dynamically type it, which is, where my heart lies. So this is showing how I can build these objects in C# and use them from C# and have both the static and dynamic worlds working together. I want to add to this showing how I can use these exact same objects from a truly dynamic language like Python. I suspect I get until C# 5.0, and I'm not going to be able to start saying truly dynamic. I'm not going to be allowed to say truly dynamic language anymore, seeing the rate at which C#'s moving to take all the good features of the dynamic languages into it. But I can still say that for one more release. And here I'm going to start up IronPython and introduce you to the wonders of a REPL. This is great. This is this place where I can type code, and it executes immediately. OK, you guys saw it earlier. But what I can easily do here, this is a fairly mature REPL. Them's fighting words. Wait, peace, peace. And in some ways, this is the point of the piece. What I'm going to do is take that code that I just built in C# and bring it into Python. So I'm going to load that assembly from the file. I'm sitting in the directory that my Visual Studio project was in, and I just loaded that assembly that I was just building for you guys live. Now I can get things off of that assembly. So here I can live create one of these bag objects. So I just created one of those bag objects that I defined in C#. I can give it a name. I can give it an age. Again, some things have been around longer than others. Let's play with the type system and pass it a string. And I can pass this same thing back to this writeBag method that you see right below. This is the exact same method that I'm calling. And now writeBag will go off and will tell me, well, Python's 17 years old. So I'm able to build these objects from Python. I can do it Python style. And in the dynamic languages, just about everything's a property bag. So here I can use any Python type. Property bag, set the name to be the DLR. DLR is about 2.5 years old, so I'm thankful I have a little bit of variety in my type system. This is where in a statically typed language I'd go back and refactor the method to accept doubles or time spans or something of that sort. I don't have to do that. And now I can write this Python object. Again, this is C# code written to expect dynamic, but it works just fine with a Python object. And one last example, and then I'm going to be done showing you the joys of Python. Python has this notion of creating truly dynamic objects built into it. So this is Python's version of the getMember method that I showed you could write yourself. And Python programmers have been writing these for, well, 17 years. And in this case, I'm going to make one that just echoes back the name that comes in with some stars around it. It's going to be a very silly class. Now I have this echo, and if I do something like get the PDC 2008 property out of it, I get back a property that's a string, a value that's the string, stars around PDC 2008. So every property that I go to get off of the object is just going to echo it back to me with strings. Now this is because Python's objects behave this way. They look for this special method named under_getAttr. And wouldn't it be great if C# could know to look for under_getAttr? And the day that I can convince Anders that under_getAttr is a good thing to go looking for, I don't know. I suspect things will freeze over and other things will fly. But by working on top of this shared system, I can make C# go looking for the under_getAttr method through the DLR, and it will work with the Python semantics, designed the way Guido intended it. So these languages can work together even when the languages are using slightly crazy features, because I happen to think we did a good job of picking the right shared operations and the right level to do those shared operations at. Okay, so that's enough of a demo, and let's go back to my main talk machine. Oh, thank you. So I have to ask the same question I did about Ruby earlier. Who's upset that they didn't just see that demo in Visual Basic? I'm told that you're very shy. Those of you who are upset that you didn't see the demo in Visual Basic, the same opportunity applies to you. I'm not picking Visual Basic because it's not my favorite language. I'm picking it because it's much easier to give a talk in 2 languages than in 4. You're going to see Visual Basic tomorrow. Paul, Vic, and Lucian are going to tell you about Visual Basic and show you how you can interoperate with this same sort of dynamic behavior there. They're also going to show you what I think is the coolest new feature in VB.NET 10, which is making line continuations go away. And that talk will be Tuesday at 5:15 p.m. Python came up with that one 17 years ago, but yeah, that's called Ruby. Sorry, getting rid of Python indentation is called Ruby. So now I want to tell you about the next part. So that part was about how we do shared dynamic dispatch. And in particular, it was about how you can play in the shared dynamic dispatch world that we have between all the different languages and the different binders. Now this is all built on top of these expression trees. I want to tell you about the expression trees. And to do this, we started with link expression trees. And I guess this story is actually kind of like the IRON as an acronym for implementation running on .NET. We started with link expression trees conceptually. In practice, we actually built a completely parallel world of expression trees that came from IronPython because we thought that dynamic languages and static languages were so different from one another, we needed our own trees because we could do it better. You're often wrong when you believe that. And what we found was our trees grew more and more like expression trees as we added more capabilities to them for what we needed in order to run dynamic languages. And we've fairly recently finally finished the unification of the two. And now I can tell the story, and you don't need to understand all of the history. Pretend we did it right and didn't make that foolish decision and started with link expression trees. All we had to do, had we done that, it would have been very simple. All we had to do was add assignment, add some control flow, including things like loops and try catches and actually goto, but you can do goto safely. C#'s shown a reasonable version of goto. Add some dynamic dispatch nodes, actually add exactly 1 dynamic dispatch node. And now we support full method bodies, and we support everything the dynamic languages need, plus we're compatible with all of that link code that came before. So let me show you what those trees look like. because this is something even in the link world, because many people weren't using trees so much, I don't think we spent enough time talking about what a useful feature these trees were. So this is showing the tree for factorial written in statically typed C#. And we'll walk through it. It starts with, of course, the if node, because that's the main body of the tree. And we have this test up here of n = 0, and that's a statically typed binary quality comparison of the integer n. The integer n. Yes, I'm truly a mathematician here. The integer in the parameter n. The integer typed parameter n with 0. The next thing we have is a return. You'll notice that one's in light blue. That's one of the new nodes that we added. That's one of the control flow nodes in order to be able to represent a full method body. You notice there's only 2 light blue nodes in here. That's kind of interesting. To return 1. Then we have the recursive method call down here. The method call node of the subtraction operation on n and 1. Again, fully statically typed. If you expand it to the full return line, you get that full bottom part of the tree. So this is the tree that represents statically the factorial function in C#. Now, when we added dynamic typing to the system, we had to make the trees look totally different, right? So here's the change. I hope you were all watching closely. Let's do it one more time. There's the change. For some reason, the return nodes got brighter. That doesn't have anything to do with the change. We added these 3 different nodes. We took the statically typed operations where we knew the types of the variables coming in and turned them into dynamically typed nodes. Again, doing the same operation, holding on to one of the standard DLR message objects of either an equality operation, a multiply operation, or a minus operation, so it can interop with all the languages, but also knowing that it came from C#, so we can use C#'s binder. That's the change to make the dynamic code work. Now in Python, this code looks shockingly similar. This is the same code for IronPython's method. It has Python's binder up here instead of C#'s. And down here, it has some slightly weird things going on. This is because factorial in Python is a lookup of a global variable. Python's global variables aren't directly represented in the tree. They happen to map almost perfectly onto a .NET static field with a property access, where we can add a little bit of extra code in the property access. So we map them onto that. We map them onto a .NET static field lookup and accessing a property on that. And that's how we represent the fact function. So we're able to represent the Python function again with its correct semantics in this same tree using the shared representation. And the Ruby tree, yet again, fairly small changes to represent Ruby. It's interesting to note here, Ruby is an expression-based language. That means that Ruby doesn't have statements. Every line in Ruby can potentially return a value. So mapping onto expression trees is actually very natural for Ruby. It doesn't need any of these new return nodes that we added. It just returns the value of the expression. And because we've maintained expression trees, and even if is an expression, it can map very nicely onto the Ruby semantics. So we're getting each of the languages represented in the trees. Let's actually talk one more thing about how we do Ruby. So here we're representing this call. Ruby, the way that Ruby handles this call, this seems to be one of the things that's different in every one of the languages, right? In Python, it's a static. In C#, it's a static method call. In Python, it's a lookup of a global variable. In Ruby, it's actually a call to a method called fact on the local this parameter that fact is expected to have coming in, or self. So each one of the languages has that difference, but we can represent that difference in the tree, and yet the trees still remain very similar, so that you can imagine code that can analyze or transform these trees could work on all of the trees. So I do need to put up one slide about different semantics, because the biggest fear that people have, and this is my biggest fear where we came with Iron, was we're going to change all of these languages and make them look the same, and then it'll be easy to have the same trees. So here's my favorite point on different semantics these days, is x times 2. Do you know different languages have different semantics for x times 2? Of course, x has to be somewhere in the neighborhood of 2 billion to get different semantics. And some of you might know why 2 billion is important. We'll get to that. In Python, 2 billion times 2 is 4 billion. Everybody shocked? In Ruby, it's 4 billion. I asked my 7-year-old daughter this question just as a sanity check. Honey, what's 2 billion times 2? 4 billion? She's like, come on, Dad, ask me a hard one. In C#, it's interesting, and I asked Anders this question just to see what he'd say, and being the smart guy he is, he said, well, in any reasonable language, it's going to be negative 294 million and something, right? Now, There are many reasons why this is a reasonable answer, despite how painful this was to explain to my 7-year-old daughter, which I did try. My 10-year-old son got it, but he's rather unusual. So the reason for this is that these are 32-bit signed integer representation. And a 32-bit signed integer, when you go above, much above 2 billion, and I wish I knew the actual number, but you go much above 2 billion, turns into a very large negative number. Yes. So it's using 2's complement arithmetic for the signed integer representation. And so it overflows to this crazy thing, which is exactly what your processor does. So C# is doing a great job of matching what your processor does. Now, this second one is actually what VB.NET will usually do by default. And my preference, if you're going to match the processor, and throw an overflow exception saying, you know what, my type can't handle this. And in C# you can get this behavior by either turning on checked in all of your code or explicitly wrapping a checked block around section. And in C# you can get the right answer, no value judgments, by typing everything as long. Of course, when your numbers get really, really, really big, that one peters out too. So the point of this different semantics wasn't to make fun of C#, although maybe it was. The point of the different semantics was, we're not going to go tell Python and Ruby, you're wrong. And 2 billion times 2 really better be negative 294 million and something. But we're also not going to go tell C# you're wrong. There are lots of good reasons why C# wants to match the machine's behavior. So even though we're running all of these languages on top of .NET, because they control their trees and they control the details of their binding, each language can have its correct semantics running on top of this. So my last slide on trees, to summarize them, trees are great because they're this lovely form. Most compiler writers work with trees all day. It's how they think about code. And trees are really easy to analyze, to transform, to compose. If you look at the cool things people have built on top of LINQ, right? There were the original things we provided of taking trees and turning them into SQL. But people have done things to do some of the parallel LINQ stuff, of making them do fun stuff running on parallel systems, or even taking LINQ code and making it run on top of a GPU by transforming the tree that comes in. There's great things you can do with the tree representation. You can do the same things with IL. It's just a lot more work. These trees are able to be shared across the different languages, and yet each language can have its own correct semantics. But what makes it worthwhile is they generate optimized machine code at the end of the day. We take this beautiful tree, and I know you can't read it, but that's the same tree I showed you early on for factorial in C#. And the CLR's JIT will turn it into optimized machine code. And you don't need to figure out how to do that. You just need to know how to work with the nice, easy-to-construct tree form. And that same machine code is collectible, which means if all the references to that code go away, if I'm doing this in one of these read-eval print loops and I generate some code and I never, ever use it again, and I don't have any references to it, the code can go away too. So trees are a great way to deal with code at runtime. And they're one of the key features for building these dynamic capabilities on top of .NET. The last big feature in the DLR is call sites. And call sites are the way that we make sure that this dynamic dispatch stuff can all run fast. Call sites are based on an old idea called a polymorphic inline cache. And I'll explain what that is as I explain call sites. We've taken that old idea and just implemented it with delegates and generics on top of the CLR. And because the CLR had delegates and generics, we were able to implement a reasonable version of this without modifying the runtime. Of course, if we ever really wanted to, we could modify the runtime and make it even better. But we have a major addition. We also have multiple languages running on top of the CLR. And this is a new idea. This is not the old idea that's been out there for a while. By having a version of call site dispatch that works well across a wide variety of real programming languages. So we have interoperability so that you can share objects across languages. So I can have an object that came from one language with a call site in another language, and I can still get all the benefits of this call site dispatch optimization. I can customize the call site dispatch to work for each language, so I can reuse it and I don't have to recreate it in each language. And I can customize it as a library writer. And this will be the very last part of my talk, where I show you how you can customize this mechanism in order to implement the absolute fastest libraries that you want to on top of it. But first, I better explain how call sites work before I tell you how you can customize them. So the idea for a call site is, let's say I have code that looks like this. And this shockingly looks similar in most of the languages. And you notice I'm not using indentation. I must have been corrupted. For if x == 0 test. And the way that we compile that to a call site in the DLR is we create a site object sitting in a static field, and we compile this into code that calls a delegate on that site object. And this target here, that's the delegate object. So what we're doing is we have this site object inside of the if. We're calling a delegate in order to do the actual operation. And that delegate points to some code that knows how to do the operation. Now, I want to point out before I explain how the operation works how nicely the static and dynamic worlds work together again here. And this is part of why we found the link trees worked so well for us. There's a lot of static type in here, even for this dynamic operation. Right? You notice, well, X is typed to object, so that's fully dynamically typed. But Y here is typed to int. Well, how can I possibly type that to int in a dynamic language? Well, the source code has it as 0. And in most languages that I know, you can represent 0 as an int. So we're able to take advantage of that static type information known at the call site and map it into our delegate. We're also, the return type of this is bool, which is the type that the if wants. Now, in most dynamic languages, an equality comparison doesn't return bool. It returns a dynamic object that you can test for truthiness, to use Stephen Colbert's words. But because we know we're in an if context, we know that we need to return a Boolean. So we can, again, have that value of static typing applied here. So we have a lot of static typing, but we're not really doing anything yet. So I need to talk about how the body of that works. And you look, the body says return site.update. And this kind of seems like I'm about to get into an infinite loop of, I call the site and it says update yourself, which is going to tell it to update itself, which could go on forever. What's going to happen when I ask the site to update itself is it's going to look at the objects that were actually passed in and generate a new delegate that's specialized to be very fast for those types. So if I call this with an integer, I'm going to generate a delegate that has a test. The very first thing it says, well, if I'm called with an integer ever again, return the integer comparison of x and y. And this is the idea of call site caches. It's that if you look at this code, if it's ever called with an integer once, the odds that the second time this is going to be called with an integer are incredibly high. So it's worth generating code that will handle an integer the second time around and handle it very fast. So that's what we're doing here, is generating code that if I get called with an integer again, life is great. Now, of course, this is a dynamic language, so I can't count on it. And I may be called with an arbitrary precision integer in the future. If I have a language that wants to handle 4 billion correctly, I might need to be prepared to be called with an arbitrary precision integer in the future. In order to do that, when I see a big integer come in, the update method gets called again, and I generate a new target. This one still knows how to handle integers, but it has new code here to handle big integers correctly and call the equality method on them. So this is the polymorphic inline cache here. This is the notion of an inline cache. In line with the call, I'm caching the information at the particular call site of what I've seen before. And the polymorphic means I'm potentially specializing the target for multiple different types. I'm specializing it here for maybe I've seen int. If I see another type, I can specialize it for that type as well. That's the way that we make the dynamic dispatch work fast. Now, how we build this, and why did I spend all this time telling you about trees? Well, all of this mechanism is built on trees. You look, this is the tree that represents that same code that I showed you for the method specialized on int. If you look at the tree, it has a few components to it. It has a test in it. In this case, the test is the type of x an integer. It has a target in it saying if it is an integer, do an integer equality comparison on the value that came in. And it has this update method. Now, by representing these things as trees, we're able to build the polymorphic cache out of this very nicely, because when the new type comes in, I can rip out the update method. I can put in a new if node, add a new test for is it a big integer, add a new target for what to do when it is a big integer, call the appropriate method, and put the update method back in. So this ability to compose these trees and rip them apart and put them together makes it very nice for building up our caching mechanism on top of. And trees are the way that you really talk to the DLR if you want it to work as fast as possible. And the way that all of our binders, the way that all of our languages communicate with trees is through a meta object. And meta object is a horrible term in one sense because it's been used for half a dozen different things. What a meta object means is, in our world, objects are about actual runtime values. Meta objects provide expressions that, when compiled, will generate actual runtime values. So meta objects work over expressions They're the kinds of things that compilers work with. Objects work on actual values. So this meta object is very simple. Our binders just need to return a meta object that has an expression representing when it's valid, if it's an integer, and a target representing what to do when it's valid. And so long as the languages can provide these to the DLR, we can generate the optimized call site code for you. And we can combine these in the various ways that I showed in order to do, some of code could come from C# and other could come from Python, and we can combine them all together. But there's one problem. There's one problem with this whole mechanism which bothers me a bit. Static objects are very fast in this world. So if I have an array list and I get x.count on it, that is going to be blindingly fast, because I have here a type test of is my parameter an array list. This is about 1 or 2 machine code instructions, depending on how the JIT's feeling. And a conversion, which the JIT will optimize away to array list, because I've done this type test up here. And an access of the property count, which can turn into, again, a single memory access on parameter x. So this can be, on the order of 3 or 4 machine code operations when I'm running on a statically typed object like an array list. That's great. That's wonderful. That's not the bad news yet. The bad news is dynamic object that I showed you, the way that you guys are all encouraged to extend the world and build your dynamic object, is a lot slower, because it still uses strings. Okay? We still generate this optimized code for it. We still generate the code, but the code says, well, if it's a dynamic object, call the getMember method on it, because that's what we're giving everybody to override, and pass it this thing that basically represents the name. Effectively, you're passing it a string that represents the name, and the person who gets that message now needs to figure out what the heck to do with that string. That's usually going to mean looking up the string in a hash table. And looking up a string in a hash table is not 3 or 4 machine code operations. It's a few orders of magnitude worse than that, depending on your hash table. So this is too bad, and as a dynamic language guy, it kind of makes me mad. Let's see, how much time do I have to finish this? Okay. So you, of course, can play too. You can build your own meta objects. You can build your own objects that work over expressions instead of over values if you want the maximum performance. You want to build a meta object that says, hey, my dynamic objects are actually immutable. I want to combine the best of fully functional languages like Haskell with the best of dynamic languages like JavaScript, because nobody's ever done that before, so I'm going to have immutable dynamic objects. I can test to see, did I pass a particular immutable object, and if so, I can encode into the target a constant saying this property will always return exactly that value. So you can get, to the degree that you can figure out how to make it run fast, you can get as much performance out of this, or sometimes even better performance out of this, than you can easily from the static world, if you're willing to generate trees. Okay, now I'm going to take 5 minutes and do the really deep dive of the deep dive before I conclude and take questions. I'm going to show you how you build a meta object. So I think the number of people in the world who need to know how to build a meta object are probably the same as the number of people in the room right now. So I'm hoping you'll follow me. This is what meta object looks like. Now, a meta object is very similar to the dynamic objects we were building earlier. Up top, it holds on to two expressions, essentially. One is the test, and one is the target. And then it has a bunch of methods, just like dynamic object had for each one of our operations. And these methods work over meta objects, meaning they work over expressions rather than working over actual runtime values. Here's how you would build your own meta object. Part 1. Part 1's the easy part. Part 1 is, here's bag. Here's the same bag I showed you before, except I'm going to implement meta object by hand on it instead of implementing dynamic object. So what you need to do is you implement the iDynamic object interface. That's easy. And you implement the one method on the iDynamic object interface, get meta object, to return your custom meta object. And for the rest of the code, you do it like you did before. You have a getMember method, a setMember method. You might get more creative here in the future, but for now, we're going to assume you did what you did before. So this is easy, right? Now you have to implement the bag meta object, and now I have to talk about expressions. So for the bag meta object, what you do is you implement each of these bind methods. So I'm going to implement the bind getMember method here. Right? This is the method that's going to show what the getMember behavior should be for my object. Now I have a little helper type in here that I want to be sure not to point out. This is just to make my code a little shorter. I take the expression that represents the current meta object and put it in self. So this is my current expression that can create me again. And then I need to generate a test. Right? I told you that's what the DLR works in. It wants a test and a target. So the test that I generate is, well, if the type of self, if the type of the object coming in that is me is a bag, great, that's my test. I know that my rule is going to be valid. So I'm providing a test that's good enough for me. My type is bag. Now the target has a lot more building up expressions by hand kind of code in it. The target builds up a call expression down here to the getMember method on bag, passing it the getMember binder in a constant. So here it's building up. This is the standard way in LINQ to create a call expression. The instance that we're passing to the call is myself converted to the type of bag that I know is safe because my test is making sure that I am an instance of the type bag. It's calling the getMember method with a constant that contains this info, which is the same thing that was passed into my binder method. Now this is where I'm not going to go deep enough to show it, but I had a question earlier of could I delegate? Could I create something that automatically delegates to other objects that are coming in as iDynamic? This is the way that you would do it. And in this world, you actually can delegate. And you're going to need to get a lot deeper into the DLR to do that correctly. But this is where you would delegate. And you can delegate extremely efficiently and create a meta object that delegates everything to a delegate that it holds inside of it. And you do that here. So I've built up the test expression. I've built up the target expression. The last thing that I do is I package them up in a meta object with the test and the target and pass that back to the DLR. And it'll take care of inserting this code into the call site to do the right sort of optimizations. So that's how you build a meta object. Some of you might want to see this 3 or 4 more times before you go to build it. That's fine. The sky's really the limit with meta object, right? The idea here was to create the simplest possible thing we could that would let you implement whatever sort of behavior you wanted to be able to. Here's a few ideas of the kinds of things that you could do with meta object. I talked about caching values. Whenever you know a member might be immutable, you can cache it. Sometimes you might know changes are rare, so you could add invalidation to your cache. With meta objects, you can build a notion of tracking a shared layout of objects. This is an old idea called hidden classes that's somewhat made it back up in currency again. But you can build these same things on top of the meta objects. You can build statically optimized code for loops to make function mappings or numeric array manipulation run very fast. IronPython and IronRuby have a lot of great ideas. And really, the idea that we're trying to hit with meta objects is that the only limit is your creativity. You can do whatever you want to with it if you can figure it out. So I want to summarize what I've talked about and hopefully not leave you with meta object as the only thing left in your brain when we go away here. So we've talked about how to get dynamic languages to run well on top of .NET with the dynamic language runtime. I've told you about how we use this shared expression trees, just the next version of LINQ that we can share across all the languages for runtime code gen that both can run very fast and be collectible. Talked about shared dynamic dispatch across languages, and I've talked about call site caching to make it all run fast. We've built languages on top of this, traditional dynamic languages like Python and Ruby, languages like C# and VB.NET that soon may get to be called, I don't know what the heck we're going to call them, as they become more and more powerful with their dynamic features. And your language could go here someday too. Underneath, these languages can talk to .NET, they can talk to JavaScript, they can talk to Python, to Office, to Ruby, and you can put your binder underneath here too. And dynamic object is actually, I think, one of the most fun places for people to start playing around with this code. And building your own binders on top of this for interesting dynamic libraries is a great place to play. So I want to this is my last slide on where do I go from here. So it kind of depends on what you want to do. If you want to build a dynamic language with the DLR, the best place to do is go to codeplex.com/DLR. That site is still very much under construction, but it'll give you pointers for where do you go today. And it'll give you a lot of promises about when you'll have better documentation and a more polished experience about where to go next for building your own language on top of the DLR. If you want to create a dynamic library for .NET 4.0, I encourage you strongly to start with dynamic object. It's amazing what sort of cool libraries you can build on top of it using dynamic object. But the sky's the limit with meta object if you're feeling we didn't give you enough rope. You can use a dynamic language. IronPython is getting very mature now. We just released IronPython 2.0 RC1, so the final 2.0 build's coming out real soon. And that's at codeplex.com/IronPython. IronRuby, you should go to John's talk today right after mine. And let's see. You can use C# 4.0 or VB.NET 10. Yeah, some minor players with the DLR. Paul and Lucian's talk on VBs tomorrow. The CTP is on your PDC drive, and Alex Turner is going to have a great lunch talk tomorrow where he's going to show using a lot of these dynamic features from Silverlight to Office to Python with C# and VB. I'd encourage that if you're interested in this stuff. And if you missed Anders' talk and therefore didn't get some of the jokes in my talk, he has a repeat of his talk on Wednesday. So thanks, and I'm happy to take questions, but I'm going to leave this slide up so that you know where you go from here. And it looks like I have oh, yes, thank you, Mahesh. So I also have stickers here of IronPython and IronRuby up front. If anybody's a big IronPython and IronRuby fan and wants stickers, feel free to come up and grab them after the question session or during the question session. Thanks. So are there any questions? Wait a second. Okay. I guess I answered them all. If you have questions, please go to the microphone instead of coming up to the stage, because I'm supposed to record them. Do you mind? I'm just trying to be well behaved here. Not usually something I'm known for.
Hi.
Yeah, questions, please. Okay.
2 questions.
Yes.
Tooling support in Visual Studio, and any plans to provide parser generator if I want to do my own language?
Great questions. So the Visual Studio support is one of my biggest embarrassments about IronPython and IronRuby so far. We do ship Visual Studio support for IronPython as part of the Visual Studio SDK. It's a sample there, so it comes with source code, which is great, but it's a sample, which is not so great. We're definitely working on making that better, but I can't promise you the date when it will be better. IronPython and IronRuby are both within the Visual Studio organization today, so if it doesn't get better, there's something really messed up. As far as a parser generator, this is a very difficult question for me to answer, so what I'm going to do is encourage you to go to the Oslo talks tomorrow. There will be very cool parser generator technology there, and it would be really silly if we couldn't figure out how to make that work together at the end of the day. So if you're interested in parser generators, definitely look for Oslo talks, particularly on textual domain-specific languages. There'll be a lot of cool stuff there about parser generators.
Thanks very much.
Yes, I guess I should. Oh, that's where the line is, so I'll take the questions over there.
So is there any way to do interoperability with CPython?
So there's the question of, can you interoperate with CPython code? I need to ask you these. So is there a particular module that you're asking for? And please don't say NumPy.
Well,
no, seriously. Is there a particular?
There are several. No, not really. We have lots of large body of CPython code.
Yes.
And we do use NumPy. We use Matplotlib. We use a bunch of stuff. We have been using something called Python.net to bridge with .NET, and I was wondering if there's anything better which we can get out of this. So
if you guys remember the talk I showed, the first slide I showed about how ugly it is to work with Python and C together, and how beautiful it is with C#. That's all true, but the Python community has built up a lot of really cool C-based libraries through the years, and it's kind of sad that we can't use them. Numeric Python is usually the one that we get asked for, which I actually wrote a long time ago, so it's the one that makes me feel most pain when people ask for it, and I can't provide it on top of IronPython. The reason that we don't provide these, it isn't any malice, mind you. It's purely that C interface is so ugly, making that work well with .NET is a lot of work. There have been external folks who've been trying to do this. There's a project, the folks who work at Resolver Systems have started a community project, and if enough community people join it, they're trying to build a bridge to bring in the CPython modules into IronPython. And I think it's great. They've had some great early demonstrations of success. And if more people join their project, they're going to be successful. That's one that we just haven't been able to put the resources behind to do it right so far.
Thank you. Thank you for the talk as well.
I guess this will be my last question.
Does the call site cache have a fixed size? Because it's also a linear search, right?
So does the call site cache have a fixed size is the question. I'm repeating the questions even though you have a microphone. And there's this concern about linear search. There's some cases of it's very interesting. Linear search, when you're executing a small number of machine code operations for each step, it's amazing how large n can get before linear search becomes a problem. We've found that going up to about 10 or 12, we're still running blindingly fast even for the 12th entry in the loop. So we do go up to, I believe our constant is currently tuned to n, although tuned to 10. And over 10, we switch to using a hash table-based algorithm. That's a number that I expect as we do our final performance tuning between now and shipping .NET 4.0 and Visual Studio 2010. Probably won't be 10 at the end of the day. Might be 8, might be 20. It's one of those constants that we tune for. But we do have a fixed size. The reason that we have the fixed size is actually not so much the cost of the linear lookup. It's actually the code gen size. There's a point when you get to having about 100 different tests, the cost of generating the code for 100 tests just isn't worth the speed up that you can get. So the main reason we do it is for code gen size. Yes, thanks. That was a great question. I guess I'll take this one as my last one. And then
okay. So given we have polymorphic inline caching, should we go ahead and implement self?
Should we implement self? If there were a large number of programmers in the world who enjoyed programming in self, the answer would be absolutely yes. If somebody wants to go out and build self on top of the DLR, I think that would be really cool. We certainly have had no compunctions about stealing good ideas that people have used in the past to make dynamic languages run very fast. The polymorphic inline cache one, I believe, actually came from Smalltalk implementations long before self. So self, in turn, stole that from other people. Some of the hidden classes ideas, I believe, first showed up in self. But a lot of these ideas are not new. The major innovation in the DLR is taking these ideas and putting them together on this common platform so that a lot of languages can use them.
Yeah, just a small caveat. I worked for David Unger for a little while.
OK. So if you want to go out and build a self-implementation, I would love to see it.
Good stuff.
I had a great talk with Dave Unger at OOPSLA, by the way, about all of this stuff.
It's great.
Thanks. Thanks, and I'll turn off my mic now.